In this video, we're introducing the inverse hyperbolic tangent function and establishing why it's useful to know about this function as a first-year calculus, physics, or engineering student. So the video is split up into chapters if you want to skip around. And we start with a basic definition of the hyperbolic tangent function and its expression in terms of exponential functions. Next, we figure out how to express the inverse hyperbolic tangent function in terms of natural logs. And because the hyperbolic tangent is expressible in terms of exponential functions, it's not too surprising that this is possible. Then we start to get into why it matters. The inverse hyperbolic tangent function is a solution to a common type of integral that we see occasionally in first-year calculus and physics courses. And finally, we're going to generalize our basic inverse hyperbolic tangent integral by expanding to integrands that have different constants floating around. So before we talk about the inverse hyperbolic tangent function, we have to start with the ordinary hyperbolic tangent function. And that begins with a reminder of our basic hyperbolic trig functions, sinh and cosh. So sinh x is 1/2 times e to the x minus e to the negative x, and cosh x is 1/2 e to the x plus e to the negative x. Now it's not surprising to learn that the hyperbolic tangent function is given by sinh divided by cosh. So that's going to be our basic definition of the hyperbolic tangent. But if we're going to attempt to invert this thing, we want to get more fundamental and replace the sinh and cosh functions with their expression in terms of exponentials. Okay, so we've got that done, and clearly the factors of 1/2 are going to cancel out of this. And we arrive at a definition of the hyperbolic tangent function purely in terms of exponential functions. Next, we're going to invert this thing. So how do we get a grip on the inverse hyperbolic tangent of x? Like any inverse function, we start by giving it a name. So y is the inverse hyperbolic tangent of x. The reason that name is useful is it allows us to invert this inverse function and rewrite this equation as hyperbolic tangent of y is equal to x. Now we can plug in our definition of hyperbolic tangent in terms of exponentials. And the goal here is to solve for y, because y is the name for the inverse hyperbolic tangent of x. And it looks like we can make progress by multiplying both sides by that denominator. This gives us e to the y minus e to the negative y equals x times the quantity e to the y plus e to the negative y. And we can distribute that x and combine like terms. And I'm going to combine all the terms on the left-hand side. So when I distribute the x to the first exponential, that's x e to the y. I'm going to subtract that from both sides, and on the left-hand side, I end up with a 1 minus x times e to the y. When we multiply the x into the second exponential, we end up with an x e to the negative y, and I subtract that from both sides. This gives me a minus the quantity 1 plus x e to the negative y, and this is all equal to 0. The next thing we can do here is get down to just one exponential function by multiplying both sides by e to the y and using exponent properties. Distributing e to the y to the first term gives me 1 minus x e to the 2y. And to the second term, I end up with an e to the negative y plus y, or e to the 0, which is just 1. So I have a minus 1 plus x there. And this is still all equal to 0. Now I'm going to add the 1 plus x to both sides and divide by the 1 minus x in front of that exponential. And I get e to the 2y is equal to 1 plus x divided by 1 minus x. And now we're getting really close to a solution. We take the natural log of both sides, and this gives me a 2y is equal to the natural log of 1 plus x divided by 1 minus x. Finally, we divide by 2, and we find that y is equal to 1/2 natural log 1 plus x divided by 1 minus x. And because y was the inverse hyperbolic tangent of x, that means the inverse hyperbolic tangent of x is 1/2 times the natural log of 1 plus x divided by 1 minus x. Now there's a slight complication to this. The natural log function is only defined if its argument is positive. So we have to think about what x values make this argument positive. And if I'm thinking about positive values of x, well, x better be less than 1, otherwise that denominator becomes negative while the numerator is positive. So we have that x is less than 1 if x is a positive number. 0 doesn't cause any problems. And then we think about what happens if x is a negative number. Well, the denominator is always going to be positive in that case, but the numerator could become negative if x was less than -1. So it's got to be bigger than that. So it turns out that our domain for the inverse hyperbolic tangent function is -1 to 1. Now, I can tell you as a physics student, I never once thought about the domain of the inverse hyperbolic tangent function. When this function crops up in a physical setting, the x always just turns out right so that you're within this domain. But as a math student, you might have to worry about it from time to time. So why should we care about such an exotic function? The answer is that it arises as a solution to a very common type of integral that we see both in first-year calculus and physics courses. I'm currently teaching first semester engineering physics and second semester calculus, and in the last few weeks, integrals of this type have popped up multiple times in both courses. In my physics course, it was a free fall with quadratic drag problem, and in my calculus course, integrals like this have popped up in the trig substitution section and the partial fractions decomposition section. So to get this integral done, we basically have two options. And option number one is to do a trigonometric substitution where we let x equal sine theta or cosine theta. We apply a Pythagorean identity, which simplifies the denominator, and we go from there. But the easiest way to solve this integral is with partial fractions decomposition. We just have to recognize that denominator is a difference of two squares, so we could write it as 1 minus x times 1 plus x. And we propose a partial fractions decomposition, a over 1 minus x plus b over 1 plus x. Multiply both sides by the least common denominator, and we get a 1 on the left-hand side. The 1 minus x cancels on the a containing term, so I have a a times 1 plus x. And the opposite thing happens with the b containing term. I have a b times 1 minus x. And we can use substitution to get a and b really quick. If I sub in x equals -1, the a containing term vanishes, and I end up with 1 equals b times 1 minus -1, or b times 2. So b is equal to 1/2. If we sub in x equals +1, the b containing term vanishes, and I end up with 1 equals a times 2, so a is 1/2. This allows us to rewrite the integrand as a 1/2 over 1 minus x plus 1/2 over 1 plus x. Now each of those terms is going to integrate to a natural log sort of thing. We end up with the natural log of the absolute value of the denominator. The first one has a bit of a complication because the derivative of 1 minus x is -1. To account for the chain rule, we end up with a -1/2 natural log absolute value 1 minus x. The second one is the easier one. There's no complication from the chain rule because the derivative of the denominator is just 1. And I end up with a 1/2 natural log absolute value 1 plus x. And we'll put a plus c on there. Now we can use log properties to combine these, and I end up with a 1/2 out in front of a natural log of 1 plus x minus a natural log of 1 minus x. Well, that becomes a natural log of 1 plus x over 1 minus x. And we're putting absolute value bars on this, plus c. And in many calculus books, this is the formula that you're going to see in the integration tables for the solution to this integral. But some of the textbooks use the inverse hyperbolic tangent instead. And the same is true of physics books and some computer algebra systems, random blog articles that you run into on the internet, Wikipedia entries. So it's important that you're able to express this as an inverse hyperbolic tangent so you get what you're looking at when you run into an article like this. So I'm wearing my math hat right now, and I'll be extra careful about the domain issues. I'm going to say if x belongs to the interval -1 to 1, in other words, it's between -1 and 1 so that this argument of the log function is always positive, then I can say the result of this integral, 1 over 1 minus x squared dx, is 1/2 natural log of 1 plus x over 1 minus x, without the absolute value bars because that argument is taken to be positive, and I'll put a plus c on there. But we just figured out that's the inverse hyperbolic tangent function. So I end up with an inverse hyperbolic tangent of x plus c. So the last thing I want to do is just generalize that result a little bit to deal with the case where the constant in the denominator is not 1. So it's convenient to express that as a square. I'm going to call it a squared. And one way to figure out how this modifies the formula is to just redo the partial fractions decomposition from scratch. It was a pretty quick one, so it's not that bad. We start by factoring the difference of two squares, a minus x, a plus x. We propose a partial fractions decomposition, a over a minus x, where that was a little a in the denominator, plus b over little a plus x. We multiply by the least common denominator. That gives us 1 on the left-hand side, and a times the quantity little a plus x, plus b times the quantity little a minus x on the right-hand side. And we use substitution again. Let x equal negative a. That's going to kill the big A containing term, and I get 1 equals b times a minus negative a, which is a 2a. So b turns out to be 1 over 2a. If we let x equal positive a, the b containing term is going to vanish, and I get a 1 equals big A times 2 little a. And I find again that big A and big B are the same. They're both 1 over 2a. So we re-express our integral with the partial fractions decomposition. Each of the terms has a factor of 1 over 2a in the numerator. So I have a 1 over 2a over little a minus x plus a 1 over 2a over little a plus x dx. And again, each of these integrates to a natural log of the denominator. And again, the one with the minus sign in it has a chain rule issue that produces a factor of negative 1. So I end up with a 1 over 2a times a negative natural log absolute value a minus x plus natural log absolute value a plus x plus c, which can be combined into a single logarithm as a natural log absolute value a plus x over a minus x. And that's a fine answer to this integral. And in fact, it's the one I'll usually write down. But again, occasionally I have my nose in a book that just loves inverse hyperbolic tangents. So we want to be able to understand what that's about. So we're going to have to think about the domain of this thing, like when can I disappear the absolute value bars? It requires that x is less than a for that denominator to be positive. And again, it requires that x is bigger than negative a for that numerator to be positive. So I could say when x belongs to the open interval negative a to a, we can disappear the absolute value bars. We find that our integral of 1 over a squared minus x squared dx is equal to 1 over 2a natural log a plus x over a minus x with no absolute value bars plus c. And now we're trying to match our definition of the inverse hyperbolic tangent function in terms of logarithms. I need to have a 1 plus a variable and a 1 minus a variable in that logarithm. So I divide the top and bottom by a, and I end up with a 1 over 2a natural log 1 plus x over 1 minus x over a plus c. So the 1/2 natural log 1 plus something divided by 1 minus something. That's our inverse hyperbolic tangent, and there's still a factor of 1 over a out in front. So I'm going to write 1 over a inverse hyperbolic tangent x over a plus c. So if I've accomplished my goal here, you'll be a little less frightened the next time a computer algebra system spits out an inverse hyperbolic tangent. Remember, if it helps you to get a grip on the problem, it's always expressible as a natural log of a ratio of these two linear factors. Let me know in the comments if you'd like me to do a video on some other exotic function, and I'll give it a shot. See you next time. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.